Today we're going to take a look at something called the derivative. Now this is going to answer a question that we really haven't asked up to this point. Let's say that you're standing on a hill and you know that every single spot on this hill has a different slope. But the question is, what's the slope where I'm standing? Now in the past, if we drew a line from where we are to somewhere else on the hill, we could find the average slope or the average rate of change of the function over that region. But that's over the entire region. We want to know what the slope is at a single point. So what we're looking for is the slope here. So let's see if we can frame this problem. Let's set up an axis and label what we have here. There's our secant line. And let's say that where we're standing is some value of x, and over here is that value of x plus a little bit. So this is delta x, just stands for a small change in x. So the two coordinates of the 2 points on the line, we're standing x, f of x, if the curve here is f of x. And of course, this spot over here is x plus delta x and f of x plus delta x. So we want to find the slope of this line. Again, the slope of this line would give us the average rate of change of that function. So if we plug in our y2 and y1 and x2 and y1, we get this. So this would be the slope of that secant line, and simplified would give us this. Now we saw in the past from our textbook, the delta x was replaced with an h a lot of times, that this was the difference quotient. Now, if we want to know what the slope of the tangent line is, or the slope of the line that's just touching the graph at the point we're standing, we need to let delta x go to 0 because we need those 2 points to be exactly the same. So if we just pick some random value for delta x, and if we watch that shrink, notice that secant line turns into a tangent line, which means that should give us the slope of the curve at that point that we're standing at. So this is the slope of the tangent line. And as you see, once we take the limit as delta x goes to 0, we'll still end up with x's in our limit here, which means we're going to end up with a new function of x. This new function is called the derivative of f with respect to x. The derivative, as we saw, was the equation for the slope of the tangent line. You can also think of the derivative as the instantaneous rate of change of the function. A lot of times we would also say that it's the rate of change of y with respect to x. Now, all three of those are saying basically the same thing, just slightly different ways of wording it. All right, so we need some new notation for this new thing we're calling the derivative. Unfortunately, there's two different notations that we use because two different mathematicians kind of came up with this about the same time. The first notation is called the prime notation, which was actually created by Isaac Newton. We put this little prime next to our function and we read this as f prime of x. Or if we're using the y notation, it would be y prime. The second notation was created by a mathematician known as Leibniz, and it's more of the slope formula. It's the change in y over the change in x. Now, the way that we read this is two different ways. This is the derivative of y with respect to x, or we just read it the way that we see it as dy dx. This is a third notation that we're not going to use until a little bit later on, but this is what's called operator notation, or the big D notation. This is read as the derivative of f with respect to x. All right, when we take our difference quotient and we do let the limit of delta x or h, whatever you're using there, go to 0, that is called the limit definition of the derivative. All right, from here, we actually need to see how to do the algebra for this, so we'll do that in a later video.